In the last session, we discussed something about the specification types, where we see the specification of the user need to communicate with the engineer, and the engineer need to communicate with the CAD tool, so that the CAD tool will be designing what kind of digital circuit is required. So with that same process, when the user is giving the specification to the engineer, so engineer need to sort out the specification. He has to represent and he has to convert the specification into the standard formats, either in terms of truth table, or in terms of Boolean equation, or in terms of a logic diagram, or in terms of state diagram. So now the very important thing is, if the specification for the AND gate, if the specification is orally explained that A, B two inputs, when any one of the input is high, output is high, or both inputs are high, output will be high. So that kind of simple specification, if it is a simple specification, can be represented in terms of truth table, or in terms of Boolean equation, or in terms of logic diagram. But if the specification is very complex, where the specification has so many inputs and the module will be doing so many operations, so in that case the truth table specification and Boolean equation specification and logic diagram specification will not be valid. So there the engineers will try to prefer that specification to represent in the form of state diagram. So for suppose if it is a processor where it has so many inputs, like a 32-bit input or 64 input, so that kind of 64 inputs they cannot keep it in the truth table, cannot represent it orally. Yes, so they cannot prefer the truth table or Boolean equation and logic diagram. They will be going straight away with the state diagram. So now in this session what we do is, if the specification in these forms and implementing them on whatever the tools that we know, whatever the tools that we know, CAD tools like Xilinx ISE design suite or Xilinx Vivado, where across these two tools what we could do is, we just simulated by writing the Verilog code, either in the behavioral or data flow or in the structural, writing the Verilog code, and after that we were simulating them, and after that we are going with the implementation, where we were going with the implementation, and we could see the RTL view. So this is how we just verified the functionality by the functionality by the CAD tools, and we will be verifying the functionality as per the requirement of that user. Because the specification is simple, so that we able to do the verification by the process of simulation, and implemented by the view we call it a RTL view. But as I said, it is a complex one, the specification is complex one. There is a easy method where we can cross verify the functionality, not with RTL view. Not with RTL view. So there is a another implementation view, we call it as a state diagram view. State diagram view. So now we just verify the functionality not through the RTL view. We have to verify the functionality by observing the state diagram view. So here the state diagram view you wanted to see, it is not possible with the Xilinx ISC design suite and the Vivado. That's why what we are trying to do is we will be going with the Quartus tool right now. So Quartus tool will be using for the design of a complex specification which is represented in terms of state diagram. So now coming to the session now, what we are trying to do is, so whatever the FSM implementation we have it for the JK flip-flop, that's what we'll be simulating in the Quartus tool. For that what we need is, we have to know how to write a Verilog code for the JK flip-flop once the specification is represented in terms of a state diagram. And also we should know the block diagram of any kind of sequential circuit, especially the sequential circuit for the JK flip-flop. And let us have a discussion on block diagram once. So if you see the block diagram for the sequential circuit and a state diagram for the JK flip-flop once, as we know, the difference between the combination circuit and sequential circuit is, the combination circuit, it will be taking the process for the doing the process for the combination of the inputs and generates the output. So previous behavior and next behavior nowhere it consider. But in the case of sequential circuit, what it will do is, the combination circuit will be keeping as it is, and whatever the output it generates by the combination circuit, it will be storing in the memory. So this is how where I have a memory. What the memory will do is, it will store the behavior, previous behavior over here. It will store the previous behavior over here. That behavior will be used over there by the same combination circuit for the next operation. So this is how the combination circuit as it is we keep it, along with we'll be keeping a memory circuit. The entire circuit we call it as a sequential circuit. Entire circuit we call it as a sequential circuit. Now the same block diagram we represent over here. The sequential circuit over here, it is nothing but as we discussed that the memory module should be there M1. I just have a notation M1, and the combination circuit over here. This is what my combination circuit over here, and where I need two outputs for the combination circuit. That's why I will be using a dedicated combination circuit C1 and C2. So this C1 C2 combinedly we call that one as a combination circuit. This is C1 is a sub combination circuit 1 and the sub combination circuit 2, C1 plus C2. That C1 plus C2 is a main combination circuit which will be kept over there. So now what C1 is the C1 responsibility and C2 responsibility, and a memory circuit which you are keeping over here, that responsibility I will discuss one by one. So if I take an example like a counter circuit, not JK flip flop, I'll take an example counter where like I will be giving a count pulse. So every positive edge I'm trying to expect like a count need to be incremented. So what I have is like presently the memory is having 000. So this is what a present state. Memory is just in the reset mode. I give reset is equal to high, so that memory is at the reset mode. So what I need to know is, the present state is nothing but one storage which has the capability of storing the state. The present state has to store the state. So it is the first state, 000 is the first state. So that state need to be held by the PS. So now I consider the PS will be a 3-bit variable, so that it is able to hold that 000. So the present state what it can do is, it will be giving a 000 state to the next state. So next state will be responsible to generate a next state like a 001. This is just a combination circuit where it will generate a 001 by taking 000. So now that 001, that count value 1, it will be loaded upon a next clock pulse, so it will be becoming like a 001. So now the present state with the same 3-bit, now it will be going with the 001 state. So this is how first state, you have any kind of representation S0 or S1 and S2. So this is how it will be changing the states. So like the particular circuit will be going from the one state to the another state based on the clock pulses coming here. So 001 it will be given as an input for the next state. Now 001 is an input to the next state. That next state generator should be a responsible to generate a next state 010. So 010. So that will be loaded into the memory upon the next clock pulse. So now the memory will be holding the next state over here 010, and that will be going again to the next state. So next state will be generated as a 011. So this is a continuous process where increment operation or any kind of combination circuit operation, it can be done based on the previous behavior. Next behavior will be generated by the combination circuit. So now we could understand that how C2 circuit and M2 circuit, sorry, C2 circuit and M1 circuit will be very important in the process of doing generating next state and present state. So now coming to the output module where output is generated, where like I'm keeping a counter circuit and where like a number of people entering into the class to be counted by the counter circuit for suppose. So everyone, first person is entered, second person is entered, third person is entered. So automatically that next state will be generating the value, it will be added over here. So that four members are counted up to now. So like that, if like 9 is the count increased, my classroom is not accommodated with the 9 people. So automatically what I need is just generating output by this block where there is a buzzer circuit I will be keeping over here. That buzzer circuit should be ringing, right? It should be becoming on the moment when there is a count reaches to the 9. The moment when count reaches to the 9. So for that what I do is sorry, like this is the 3 bit, right? So when count reaches to the 6, let us suppose count reaches to the 6, let us suppose. So now 110, when it reaches to the count 110, so what I'm expecting, I just observed that the accommodation across the classroom is only 6. More than 6 is not accommodated, so that I keep this buzzer at the output outside where across the door. So when the buzzer is ringing, it means that there is no place in the auditorium or class, so that no one should not enter, right? So for that sake what I do is I will be keeping some circuit over here. I will be keeping this kind of AND gate over here, 3 input AND gate over here, 3 input AND gate over here. So here whatever the present state is having, present state let us suppose it is 110, 110. So that present state will be going through the output generator. So 110, once it come to the 110, so I will be keeping a bubble over here. This kind of combination circuit I will be implementing here. So the moment 110 come over here, automatically this circuit will be generating 1. So automatically 1 is generated, this buzzer becoming on. So that indication what we are expecting, it will be provided. So we understood that main important purpose of like output module is to generate whatever the required output we have. So like that we need to have a output generator as a called combination circuit 1, and the next state generator we call it as a combination circuit 2, and a memory circuit we just keep it a notation with the M1. So these 3 modules combinedly we keep it and represent it as a block diagram for any kind of sequential circuit, right? And coming to the state diagram, where state diagram will be combination of states. So if you see the counter states, S0 is the first state, it will go to the S1, and it will go to the S2, it will go to the S3, like that it will be having n states. And if it is a JK flip-flop, there will be 2 states, because like a JK flip-flop will be holding either logic 1 or logic 0. So either it will go to that S0 state and it will come to the S1 state. So it will be switching from one state to the another state among the 2 states, between the 2 states. So here we should know something about the state diagram is where S0, S1 is the notations we understand, we can understand, but the tool cannot understand. So what we have to do is whatever the notations of states that we have to define it as a parameters, and we have to give some parameters as a symbols here. If you have three states, let us suppose 4 states, 3 states, let us suppose. So now what I do is, if I have 3 states, like 3 teams I have, if I have 2 teams, what I do is I will be putting a coin over here. I will be keeping one variable over here, and whatever the symbols that I can generate with the coin, right, either like 0 or 1. So two symbols can be generated. So I will assign like S0 to this one and assign 1 to this one. If I have three states S3, S3, so there are two symbols which can generated by the one coin, either tail and head. It's not enough. What I do is I will be keeping another variable over here, and with another variable tile head tile. So like that there will be 0 0 0 1 1 0 and 1 1. There are four possibilities that I will get it with the two variables that I will be dedicatedly assigning for S0 and S1 and S3. So this is the basic knowledge that we have to know about the state diagram and block diagram, where I'm trying to use the same concept in the JK flip-flop implementation. So coming to the JK flip-flop implementation here. So as we know, there are two inputs for the JK flip-flop, J and K, and clock and reset, and there will be output. So not only one output, there is a Q and Q bar. These are the two outputs. And as it is, it will be combination of a combination circuit and a sequential memory. The combination circuit again I will be dividing into the two circuits, one C1 and C2. The C1 will be responsible to generate the output, C2 is the responsible to generate a next state, and the memory is the responsibility to take a next state and generating the present state. And coming to the state diagram, where I know the JK flip flop will be having two states, either it can hold a logic 0 or logic 1. When it holds a logic 0, I will be considering it is in the S0 state. If it is holding like S1, it will be there in the S1 state. So now what I have the state diagram for the JK flip flop is, it is in the S0 state, it can move to the S1 state for the given combinations 1 0 or 1 1. And in the same way, it can be in the same state, for the given combination 0 0 JK combinations. These are the JK combinations, either JK, it might be 0 0 or 0 1. And when it is in the S1 state, there will be a possibilities of JK for the given combinations. If it is a 1 0 or 0 0, it may be in the S1 state. So it will be going to the S2 state. It will be going to the S2 state, sorry, S1 to S0 state for the given combinations 0 1 or 1 1. So as we know, these different combinations where it will be moving from the one state to the another state, S0 is the one state and S1 is the another state for the JK flip-flop. And now to write a Verilog code, I need these two informations about the block diagram and about the state diagram. And whatever the code I'm trying to write it, just we have a discussion on that. So what I'm trying to do is, I will be generating a .v file that I will be providing that as input to the CAD tool. So after like CAD tool will go through that all the instructions, that CAD tool will be generating a JK flip-flop. And what will be the extra feature that will be having the Quartus tool is, so we can see the implemented view, not only RTL, we can see the state diagram also. So that will be the extra feature that we'll be having. Let us see that we implement using the .v file, we'll implement the JK flip-flop, and we'll see that RTL view and the state diagram view both. So now coming to the .v file, what I'm trying to do is, I will be splitting that entire program into the three modules. This is one block, this is the second block, this is the third block. Right, this is the second block, and this is the third block. Yes. So in the first case where I'm trying to use the module name is K1. K1 is your wish. You can use that any name. Module name is any name. Module name, and whatever the ports that I have with the JK flip-flop. This is the JK flip-flop. I will be having JK inputs, and a clock input, and a reset input, and the Q is the one output, and Q bar is the another output. So this is the JK flip-flop, and same JK flip-flop functionality will mention it here, we'll define it over here. So we define it over here. So from the beginning, what I'm trying to do is I'm just defining the module name K1 and with the ports JK, clock, reset, Q bar. So that is in the first line. So module name, module ports, and we declare JK clock reset as input ports and Q bar. These two are output ports. Yes, and wherever we have two modules and having the intermediate variables over here, intermediate connections over here, so we should define with the net data type. So where what I am trying to do is I will be defining a net data type over here. So this is what my net data type. This is what net data type. This is also we call it as a net data type because the next state and the present state, these are the two variables we didn't declare at. It's not a input variable, it's not a output variable. So that's why we will be defining as a intermediate variables. So using the net data type register. So now the present state and next state, these two are present state and next state, these two are like a one storage. We keep it as a bucket. Next state, what it will generate that output, it will be keeping in this bucket and it will be taking by the memory. And in the same way, whatever the memory it generates that output, it holds the output, it will be kept in this bucket and this will be taken by the next state generator and output generator. As simple as much. And if you treat that one as a bucket, and we should define that what will be the storage and what will be the size of the bucket, what will be the size of the storage. Yes, so now what we do is S0 and S1, as I know that next state might be, means state might be it is in the S0 or S1, right? So first initially I know that the memory should be at S0, memory should be S0, so present state should be S0, so means that present state over here it should be S0, means in this bucket the S0 value should be there. So practically it is not possible and present state with the value of S0. So tool cannot understand the notation of S0. For understanding, what we do is S0 will be represented as a symbol and S1 also is represented as a symbol. That symbol assignment that I will be keeping in the bucket. Yes. So S0 will be represented, let us suppose with 1 bit 0 and this is represented with the 1 bit 1. Means tile is assigned to him and head is assigned to him. Because I have two teams, what I do is tile is assigned to him and head is assigned to him. This is the symbol dedicatedly we are assigning. Wherever we have 0, that is the representation of S0, and wherever we have the 1, that is the representation with the S1. But the problem with assigning a logic 1 and logic 0 as a symbols to the S0 is we have multiple times we are using 1 and zeros, so that a tool has confusion that it cannot generate a state diagram view for the given assignment. So what I do is I will be assigning not with the 1 bit symbols, I will be assigning with the 2 bit symbols. So 2 bit symbols in the sense, so 2 bit symbols in the sense, what I'm trying to do is S0 is assigned with the 2 tick B00 and this is also a 2 tick B01, means B01 means, so I will be using like two coins, not one coin. Previously one coin was used when dial is the indication of, that for the S0 and the head is for S1. But we have that same repeated notations for other variables also. So that's why what I'm trying to do is to do the proper assignment, what I'm using like two coins I'm using. So 0 0 coin, two coins. When I have a tile, so that is the indication of the S0. So tile head, that is the indication for the 1. If I have more than two states, if I have third state also, I can assign that a 2 tick be 10 for the third state and a 2 tick be 11 for the fourth state. If I have 5 states, what I do is I will be changing the assignment now with not 2 coins, I have to go with the 3 coins now. So I have to use like 3 tick 0 0 0 0 0 1 0 0 1 0 1 0, like that. I have to go with the new kind of assignment by increasing that number of variables across the each assignment. Yes. So now, as of now, I prefer this one. So where S0 is the representation with the 2 bit symbol and S1 is the representation with the 2 bit symbol. So now once I keep that S0 into this bucket, S0 is the size of 2 bit, so I have to make sure the bucket over here it should be the size of 2 bit. So for that what I do is the present state and next state I represent as a net data types registers where the size of the register should be 2 bit. If I go with the 3 bit assignment, so if I have 5 states, so 3 tick be 000 001. If I go with that kind of assignment where each variable S0 will be the 3 bit symbol, so S0 once I keep it in the present state, I have to keep it a 3 bit. So for that what I do is at the register I have to keep it at the size of 2 down to 0. So that what kind of present state next state size we are keeping, that based on that what kind of assignments we have used. Yes, after that we have to go with the parameter assignment. So S0 what we have assigned, tool should know that. So tool only knows that 0 0 and 0 1 1 0, that kind of input combinations, but what should we know is S0 and S1, that is what notations we are using. S0 and S1, these are the notations we are using. These are all notations we are using. That notations will be assigned with us some parameters over here. 0 0 is the symbol for the S0 notation, and 0 1 for the S1 notations, which are declared as a parameters, that in the fourth step. Yes. So as of now, inputs are declared, outputs are declared, and net data types are declared, and we declared S0 and S1. These are the two states we are using in the state diagram as a parameters with some symbols over here. 0 0 is a symbol for the S0, 0 1 is the symbol for the S1. Yes. Now finally we use the end module. We don't have any confusion with this one, and with these and all very clear. And now we can see three procedure blocks. So this is the first procedure block, always at the rate positive edge of clock, and always at the rate present state, always at the present state. So whenever we have always statement, that is the statement which indicates that we are trying to convey a procedure for any kind of module. Yes. So now as we see, as we see as we see, we have three blocks over here in the block diagram, entire block diagram. We have three blocks, sub blocks, C1 and C2 and a memory, right? So now once we have three blocks over here, there should be three modules with this three different processes need to be carried. So that same procedure, each procedure we have to define it over here in the .p file. So what I am trying to do is I will be defining the memory module M1 over here. So this is what my definition for the memory module across the procedure block, always at the rate positive edge of clock. In between I have all statements, right? The same way I will be having a combination circuit 2 which generates the next state. The procedure over here which will be defined over here in the C2 block, and here this is what my C1 block. So the always statements I have to write it for the three times to define a M1 module once, and C2 module once, and C1 module once. And now let us go into the details about like M1 module definition. So here I am defining the memory module. Here I am defining the memory module. So how the memory module is defined is, while we are defining, I am going with always at the rate positive edge of clock, and some if statements I am trying to write. There in the if statement I have a syntax that if statement, if condition. So this is called condition, and this is called statement, right? So one thing we have to know is, if it is a AND gate, always at the rate pos edge of clock, begin if a is equal to 1 tick b 1 and b is equal to 1 tick b1, then y is equal to 1. So where we know this is what my condition and this is what my statement. So what condition says is, in the conditions will be having all set of inputs and the statement will be having set of outputs. So in the same way, in the statement we have to define all outputs. Yes. So in the memory module, if you see, for the memory module, if you see, outputs are outputs are outputs are memory module outputs are present state. Outputs are present state. Now if you see, in the procedure block everywhere we have to define what my output is. So what my output is. So here y is equal to what? That's what we defined in the always statements, in the procedural statements. The same way we have to define what present state need to be. So we need to concentrate on this port. So because this is the memory module which generates the output over here, that is what your present state. So we have to do the statements, we have to write the statements everywhere. For every condition, what should be my present state. So here also, when the reset is given, what should be my present state. If reset is not given, what will be my present state. So like that, multiple statements I am trying to mention it over here to define my output. Output is present state. So here the present state is equal to S0 once and the present state is equal to next state once. So what is this to? What is this to? So he is saying that when there is a reset, reset is given. When the reset is given, so the particular memory need to start with the count 000 if it is a counter circuit. In the similar fashion, if it is a memory, irrespective of the state which is having, that particular memory, it should come to the zero state. That is called your S0. So that's what I'm trying to mention. If there is a reset, the output, the present state should come to the S0. Present state should come to the S0. Otherwise, it should go to the next state. Otherwise, it goes to the next state. Means this present state need to be updated with the next state. Previously, we discussed, right? 000 is the count. Next state, the count value is 001. This value will be updated. It means the next state value will be updated into the present state. So I write like a present state equal to next state, right? Y is equal to A and B or something, right? Present state is equal to next state. And few people have a confusion that instead of like ps is equal to ns, they will write like ns is equal to ps. So you should not have any confusion, because like while you are declaring and while you are defining a memory module, we need to have a statements something equal to that output equal to. So here output is ps, means that ps equal to something, we have to write it for sure. So ps equal to something, that's what we have to clear, like means everywhere ps equal to what we have to define. So in the similar fashion, if it is the next state module, we need to put all the conditions and finally we have to put all the statements. In that all statements, we just need to know this next state generator need to take a present state as input and need to generate a next state. Means the output for the next state generator is ns. So here every statement ns equal to what? That's what will be defined over here in the all statements. Yes, so here coming to the third module where the outputs are Q and Q bar, means we will be writing all the conditions and finally we will be writing the statements. These are all statements over here, and what Q equal to and what Q bar equal to. So we need to bother about these two people, what EMO, like what happening, that's what we have to define. So here how we are defining like ns, what happening to the ns. So here we are defining what happening to the ps. Here we have to define what happening to the q and q bar, because these are the three possible outputs that we'll be having for the three combinations, right? Three blocks, right? So coming to the always statement, so here we are using positive edge of clock. When the positive edge of clock is given to this memory module, so here the memory module is doing the function. So in the similar fashion, right, I will be defining a combination circuit 2 and 1. So here I am defining a combination circuit 2. What combination circuit is doing is always at the rate positive edge of clock was the input, because it is having a positive edge of clock. Here that input is present state. Based on the present state, it is doing the operation. So that's why always at the rate the present state is what I am defining in the sensitive list, and the present state ps will be taken as a cases. There are two cases, s0 and s1. Sorry, this is s1. Sorry, this is s1. When it is there in the s0, when it is there in the s0, There, based on the condition j equal to 1 and k equal to 0, j is equal to 1 and k equal to 0, and or j equal to 1 and k equal to 1, either this condition or this condition. I have like a combination of the condition 1 and condition 2 I am taking. This is what your combined condition. For this condition there will be statement is, this is what we call it as a statement, and already discussed that a statement should be a definition of what kind of output we have to generate. So here the output is next state, so that the next state should be what. So when it is in the S0, next state for sure it will be S1. So next state will be S1. Else next state will be S0. Next state will be S0. Otherwise it has to be there in the same state. That is what the definition over there when it is in the S0. The same way when it is in the S1, so when it is in the S1, we have to give the conditions that either like a 0 1 condition or 1 0 condition, 0 1 condition or 1 1 condition, right? For the two conditions, combined condition of C, for this combined condition, what will be the statement, we are trying to define it over here. The statement is next state, when it is in this state, next state will be S0, or else like it will be there in the same state, right? So this is how we define two states. When it is in the S0, what happening to the next state, and when it is in the S1, what happening to the next state. So here that we will be taking like a present state as a case, and we are declaring the next state, so that the correlation between the next state and the present state, the relation will be defined over here. So by taking a present state, how the next state is generated, everything will be explained over here. And coming to this block where we just need to bother about like how the outputs are generated. So here always at the rate again, like I will be taking a present state as a state, so that I will be having only input like present state, and there is some possibilities that the input is also taken. So now here in the sensitive list, in few cases I will be adding like a j and k. Here in the few cases I will be adding j and k, so you need not to add also in few cases. So either like a output generator need to have j and k both inputs, or neglect them. Based on that we will be having two cases, whether it is a meal emission or Moore emission. So like a present state and jk, and for that what kind of like operations will be done here, and you have a jk present state, what kind of operations it is trying to do is also we define. So when it is in the S0 and S1 again, if it is in S0 state, memory is in S0 state, memory is S0 in the sense it is holding S0, means it is holding 0. For sure it has to be q value is 0 and q bar value be 1. That's what we are trying to define. So the q is equal to 0 and q bar equal to 1. That's what happening here. In the similar fashion, when it is in the S1 in the sense it will be holding 1, so q will be 1 and q bar will be 0. So q will be 1 and q bar will be 0. So that is how we have declared that outputs, right, when it is in the state S0 and S1. So these three blocks, procedure blocks, if you add it, it has covered like all the information about like a block diagram of your JK flip-flop. So once it is done, like a programming for the JK flip-flop is done, and we have to implement it. So now let us have the implementation on the Quartus tool for the JK specification. So let us see that one. So now coming to the Quartus tool, I will be just opening the Quartus tool now.